Tonight's presentation is titled How to Destroy Your Engine in 1 Minute. And our presenter is Mr. Mike Bush. Mike is the founder of Savvy Aircraft Maintenance Management. He also holds a CFI certificate and an AMP certificate with inspection authorization. He's an author for numerous aviation publications, including the EAA Sport Aviation magazine. Mike was recognized by the FAA as the Aviation Maintenance Technician of the Year in 2008. We're so lucky to have Mike a part of the EAA webinar series on a regular basis, giving us information that is most useful and most interesting. I know tonight's presentation, when I first learned of the title, I thought, now that's an interesting one. I can't wait to hear that one. So with that, Mike, we sure do appreciate you being with us tonight, and I'm going to turn control of the presentation over to you.
Good evening, Tim, and good evening, everybody. What we're going to be talking about tonight with this interesting title are the subjects of abnormal combustion events, detonation and pre-ignition in particular, that have the potential of destroying engines very quickly. In fact, you'll see exactly how quickly. We've got some interesting pictures to show you tonight. And we'll be focusing on the role of cylinder head temperature in detecting these conditions and learning how to detect them early enough that by appropriate pilot action we can prevent the engines from being destroyed in 1 minute. So let me just launch into this thing, and we'll start talking about detonation, which is one of the two abnormal combustion phenomena that we're going to be focusing on tonight. Detonation is something that's caused by excessive peak pressure and or temperature in the combustion chamber. And if the pressure or temperature are high enough, it causes the combustion process, which is normally a nice, smooth, burning flame front that moves across the combustion chamber, to be abnormal and to have localized and abnormal rapid combustion events, sort of spontaneous local combustion. And it's a phenomenon that generates shock waves. I'll actually show those to you, that destroy the protective boundary layer that protect the combustion chamber components, in particular the piston and the cylinder head, which are both made of aluminum, from melting. If you think about it, peak temperatures in a combustion chamber typically reach close to 4,000 degrees Fahrenheit during the hottest part of the combustion event. And the melting point of the aluminum alloy that is used in our cylinder heads and our pistons is much lower than that. So, you know, at first glance, it seems like a miracle that an aluminum cylinder head and an aluminum piston can actually survive that. And the thing that lets them survive that is that a boundary layer forms such that although in the middle of the combustion chamber we have temperatures close to 4,000 degrees, at the surface of the cylinder head and at the surface of the piston, the temperatures don't get nearly that high because of this protective boundary layer. It's much like the boundary layer that forms over a wing in flight. Ever notice that if your airplane is dirty and you fly through rain, it doesn't get cleaner? And that's because there's this boundary layer over the wing that protects it. In this case, protects it from getting washed. But the boundary layer is absolutely crucial for the survival of the piston and the cylinder head. And when we get these localized shock waves caused by detonation, that boundary layer is breached, and the piston and cylinder head are exposed to temperatures much higher than what they're designed to be able to accept. Heavy detonation can result in melting of the piston, destruction of the cylinder in a matter of minutes, and you'll see a number of examples of that tonight before we're done. Now, the classic explanation of detonation that we typically get in pilot training and that mechanics typically get when they go through A&P training is something like this. This is sort of a classic old diagram that comes out of textbooks, and it shows normal combustion as being a forceful but steady push down on the piston, and that detonation is when the fuel-air mixture explodes violently rather than burning smoothly. That's the way I was taught in pilot training, and that's what the textbooks for mechanics say when I went through A&P training. And it turns out that's just wrong. That's just the wrong picture. That's not the way detonation is at all. It's not a binary event. It's not a situation where the cylinder is either detonating or not. The more accurate picture of detonation goes something like this. We start off with a spark on the spark plug, which nucleates the combustion event. That combustion nucleus that starts at the spark plug, and this diagram is sort of simplified, it's just showing one spark plug rather than the two that we have in our piston aircraft engines. But from that nucleus generated by the spark, we develop a flame front that burns smoothly and transitions across the combustion chamber. And in normal combustion, that flame front moves smoothly until all of the fuel-air mixture has been burned. And it's a process that, you know, it happens pretty rapidly. It takes, I don't know, about a 50th of a second from the time the spark fires to the time that the combustion event is over. And in our piston aircraft engines, we actually have two spark plugs and two nuclei for the flame front, and we have two fronts that sort of burn towards the center of the combustion chamber. But it's a relatively smooth and well-controlled event. When detonation occurs, because the temperature and or pressure in the combustion chamber is higher than the fuel octane rating can sustain, we get something more like this, where the unburned mixture that hasn't yet been overrun by the flame front, we call it end gases, they start burning spontaneously and somewhat violently, and we have all these little localized combustion events rather than this one smooth flame front. And the shock waves that are set up by those spontaneous combustion events in the end gases is what breaches the boundary layer and causes the cylinder head and piston to start getting compromised. Nowadays, we have the ability to actually stick pressure sensors in the combustion chamber. My friend George Brawley down in Ada, Oklahoma, who has probably the most advanced piston aircraft engine test stand in the universe, when he puts an engine in the test cell for test run, he installs these tricked out spark plugs that actually have pressure sensors built into them. And all of these pressure sensors are wired up to a big bank of computers, and we can actually watch in real time as the engine is running. We can watch the pressure pulses occur in the cylinders. It's really very interesting, and you learn a lot about what goes on inside aircraft engines by hanging around a test cell like that for a little while. And in the normal combustion event, that pressure trace is fairly smooth. It starts out when the spark fires, typically 20 to 25 degrees before top dead center. It rises smoothly to a peak, and which normally occurs around 18, 20 degrees after top dead center, and then it starts falling back down. If we get into light detonation, which is what's sort of depicted in this middle graph, we start seeing a little bit of ringing in that pressure pulse. And then as the detonation gets heavier and heavier, that ringing starts to get much greater, and you can actually see the shock waves in that pressure trace. And we start getting localized, very high pressure pulses caused by this uncontrolled combustion. And so the right-hand graph depicts what heavy detonation would look like. The middle graph, what light detonation would look like. And the left one, normal combustion with no detectable detonation going on. And it's important to understand that detonation, again, is not a binary thing. It comes in all sorts of flavors, from light to medium to heavy. And light detonation is something that happens, fairly commonly. It doesn't hurt anything. Actually, all it does is it keeps the combustion chamber nice and clean. But when it progresses into medium and heavy detonation, then it can start damaging things. Usually the first thing it damages are the spark plugs, because the spark plug, what are called the nose core insulators, the white ceramic part of the business end of a spark plug, tend to fracture when these pressure pulses hit them. But as it gets heavier, it can start damaging pistons and cylinder heads because they're being exposed to higher temperatures than they're designed to deal with. And so we need to make sure that we don't let heavy detonation occur, and that we take whatever action, if it does start to occur, we take whatever action we need to stop it very quickly. Because if it is allowed to go on for any length of time, it can start doing very serious damage. Now let's talk about pre-ignition. Pre-ignition is a very different phenomenon than detonation. The two are often confused, and I'll explain why in a minute. But pre-ignition is caused when the flame front in the cylinder is initiated, is nucleated prior to the time the spark plug fires. In other words, the flame front starts way too early, typically long before the piston gets up to top dead center. And so it's trying to push the piston in the wrong direction, and it's creating tremendous stresses in the cylinder, in the combustion chamber. And what causes pre-ignition is something in the combustion chamber that has overheated, and is overheated to the point that it starts glowing and acts like a glow plug in a diesel engine. So it actually ignites the fuel-air mixture before we're ready for it to be ignited, before the spark plug fires. And there are various things in a combustion chamber that can overheat. But whatever it is that overheats and starts to glow causes this pre-ignition thing. And pre-ignition is extremely violent. It's a much, much more violent phenomenon than detonation. No piston aircraft engine cylinder can withstand pre-ignition for more than a minute or so. So if it happens, it will take out the cylinder very, very quickly. Typically, as I say, in 1 minute flat, which is sort of where I got the title of tonight's webinar. Now, detonation and pre-ignition are distinctly different phenomena. Detonation is something that goes wrong during the normal combustion time. Pre-ignition is when a combustion is initiated well before it's supposed to be, well before the spark plug fires. So these are two very different phenomena. But the thing that can get confusing is that detonation can morph into pre-ignition. In other words, we can have detonation in the cylinder that grows into heavy detonation, causes things in the cylinder to get way too hot, and eventually something starts glowing to the point where it starts causing pre-ignition. All of the pre-ignition events that I have actually analyzed typically started with detonation that morphed into pre-ignition. And when we do a forensic teardown of a cylinder after one of these events, we can very clearly see certain signatures that indicate that detonation was going on and certain other signatures that indicate that pre-ignition was going on. And I'll show you a bunch of pictures so you know exactly what I'm talking about, and you will become a trained forensic analyst. Let me show you a couple of actual events. This is one that happened years ago, probably 5 years ago. It involved a Cirrus SR-20 in the UK, if I recall correctly. What we're looking at is a graph of the cylinder head temperatures that occurred in this engine, and this was done a long time ago when the software we used to plot this stuff out was very, very primitive. Hence, the graph is kind of primitive. Please excuse that. As we move towards more current things, you'll see that our software has got a whole lot fancier. But in any case, as you can see, the pilot started the engine at about, I don't know, 10:28 in the morning, and by about 10:40, he was at the end of the runway. He applied takeoff power, and all of the cylinder head temperatures came up as you would normally expect them to do upon application of takeoff power, up to 350 to 370 degrees Fahrenheit, kind of the normal range for these things, except for one rogue cylinder. It turned out to be cylinder number 5, and upon application of takeoff power, the cylinder head temperature on cylinder number 5 started rising very, very rapidly and started reaching levels that the cylinder head temperature should never be allowed to reach. Just for reference, I've put a couple of horizontal reference lines on this graph, one at 400 degrees Fahrenheit, which is sort of my magic press the panic button level. We'll talk about that. And 460 Fahrenheit, which is Continental's official cylinder head red line. And as you can see, the CHT on number 5 rose quite rapidly, past 400, past 460, and got up to 500 degrees, at which point it did something that seems a little weird at first. It flat topped at 500 degrees. Well, it didn't really. It turns out that the Aviation MFD in this Cirrus that captures all the engine data, the guys who wrote the software for that it never occurred to them that cylinder head temperature could ever get hotter than 500 degrees. So the instrument won't record temperatures higher than that. What actually happened, of course, was the CHT continued up to a peak that we can't tell exactly, but it's somewhere in the vicinity of 550, at which point the piston melted and the cylinder shut down, and of course the CHT then proceeded to crash down back to Earth. The engine started shaking like crazy because it was running on 5 cylinders. The pilot pulled the power back and wound up putting the airplane back down on the runway. So this was a pre-ignition event, because only pre-ignition can cause a cylinder head temperature to rise at that astronomical rate. If we look a little bit closer at this thing, from the time that number 5 cylinder head temperature passed 400 degrees, which is my magic number where I say, hey, something's seriously wrong here, to the time that it reached whatever that peak temperature was, roughly 550 degrees, it was rising faster than 1 degree per second. And to get from 400 to 550 would have taken about 150 seconds, something less than 2 minutes. So if the pilot had been programmed to watch for cylinder head temperature above 400 degrees, which obviously he wasn't, he would have had less than 2 minutes from the time the cylinder head temperature crossed that threshold to the time the piston melted. He would have had less than 2 minutes, closer actually probably to 1.5 minutes, to react and do something to prevent the cylinder from being destroyed. Obviously he didn't. This is a picture of the piston that came out of that cylinder. And the two features I want to bring your attention to on this picture, and you'll see similar things again later. The top of the piston crown, has all of these little indentations that kind of looks like somebody beat on it with a hammer. And those are classic detonation signatures. Those are places where the boundary layer was breached, and that little tiny localized pockets of that piston crown were exposed to temperatures sufficiently high that the aluminum started to melt. The other feature that's more obvious here is the phenomenon we call corner melting, and that's when the pre-ignition took hold, and the overall temperature in the combustion chamber got so hot that the piston just started to go into meltdown, and the place that it usually goes into meltdown is around the corners of the piston. And this is, when we see this, we call it corner melting. So the damage to this piston happened pretty much in 2 phases. It started out as detonation and gave that pockmarked appearance to the top of the piston crown, and then it morphed into pre-ignition, where everything got so hot that the piston went into sort of a general meltdown condition, and that caused the corner melting. Here's another flight. I apologize for the busy appearance of this chart. This one actually came out of George Brawley's test cell, and it's a little hard to follow, and I won't ask you to follow it, but I'll just point out the sort of the key interesting points here, where you can see the cylinder head temperature on this particular cylinder. Again, the yellow star is where it crossed a 400 degree cylinder head temperature threshold. The red star, which occurs up around 560 or 570, is where the piston melted, and in this case it actually melted a hole right down into the middle of the piston. That from the 400 degree point to the piston being holed took only about a minute. It happened very rapidly, even more rapidly than the previous one that you just saw. And then, of course, once the piston was holed, EGT dropped literally vertically to 0, and the cylinder head temperature, which had some thermal mass to it, started falling pretty rapidly and started approaching outside air temperature. Here's what that piston looked like. You can see that it did sustain some corner melting, but it melted a hole in the middle of the piston, and once that hole broke through, of course, everything quit, and everything, combustion stopped instantly, and the melting process stopped. So this was pretty dramatic. Now I'll move on to an event that's a little bit different in character, and that happened about 2 weeks ago. It's an airplane in Florida, and the next 4 slides, this one and the next 3 slides, are slides from our Savvy analysis system, you'll see that our software got a whole lot more sophisticated, and the charts are a whole lot prettier than they used to be. This is our latest state-of-the-art stuff. And I'm not going to ask you to look through all these details. This is an analysis that we prepared for the aircraft owner. But this particular chart is showing the entire flight from the time he started the engine to the time he declared an emergency and put the airplane down at, actually, I think it was at Lakeland, Florida, where the airplane got put down. It wasn't his original destination, but it was where he wound up. In the top chart, we're plotting exhaust gas temperatures, EGTs, and we're plotting fuel flow. And on the bottom chart, we're plotting cylinder head temperatures, and that red horizontal line on the bottom chart is the 400-degree mark. And if you look at the bottom chart, you'll see that the number 2 cylinder had a higher CHT than any of the others. It had a cooling air problem. The number 2 cylinders on those engines frequently run hotter because they're in a bad location right by the oil cooler. And but everything was fairly steady state up until about 40 minutes after takeoff, when the number 2 cylinder head temperature gradually started to rise above the rest of the pack, and it took about 10 minutes or so for it to get to 400 degrees. This was obviously not a pre-ignition event. This was a slow, majestic climb rather than a rapid one. So it was a detonation event. And then eventually it rose up to above the manufacturer's red line, got up to 466 degrees, at which point the head separated from the barrel. The cylinder shut down in a very spectacular way, and the pilot made an emergency landing. At any rate, let me start zooming in on this thing so you can see the event a little bit more closely. This is the area that I circled here, where the interesting stuff was going on. It's about 17 minutes from the time that cylinder number 2 CHT started rising to the time that the cylinder shut down in a very destructive and spectacular way. Here's a kind of a close-up of that, and you can see that over a period of 5.5 minutes, the CHT rose above 400 degrees. It took 5.5 minutes for it to finally get to 6 degrees over the manufacturer's red line, at which point the cylinder failed. And if you notice in the upper chart where it's showing the pilot's actions of going full rich and then throttling back, he took absolutely no action until after the cylinder was destroyed. He had 17 minutes, arguably, at a minimum of 5.5 minutes to notice that something really bad was happening, and he didn't. He just was cruising along merrily until the cylinder destroyed itself. And this was in an airplane with a big glass cockpit, instrumented up the kazoo. I know the avionics in this airplane, and the cylinder head temperature bar changes from green to yellow at 420 degrees, which is really higher than I would like to see it, but that's how the software is programmed. And then it turns to red at 460 degrees. And so this thing was in the yellow for 5 minutes or so before, without him noticing anything. And finally, by the time it hit red, the cylinder only had seconds to live, obviously, and then it died. And again, in the upper chart, which is showing EGTs, you can see how once the cylinder failed, the EGT dropped vertically to 0, and then the cylinder head temperature, drifted down to ambient. And here's an even closer look of that critical period where the cylinder failed, and you can see actually from the time the piston started to melt to the time that the pilot decided something was wrong and went full rich and throttled back was a couple of minutes. So he was pretty lethargic about dealing with this, and clearly not fast enough to get the job done. Here's the barrel of that cylinder. You'll notice that there is no cylinder head. The cylinder head and the cylinder barrel separated, which is what shut the cylinder down. I don't want you to get the wrong picture. When I said the head separated from the barrel, I don't mean it went like flying, you know, through the cowling and dropped into the Okefenokee swamp or anything. When the head separates, it separates about 1/4 of an inch, which obviously is enough to totally shut down the cylinder, but the head is still being held quite firmly by the induction tubes and the exhaust risers and stuff like that. So it's not going anywhere. But the head to barrel junction failed here, and a gap opened up around between the barrel and the cylinder head. Of course, the compression went to 0 and combustion stopped. Here's a close-up of the cylinder head, which of course is separated from the barrel. Notice the detonation signatures on the cylinder head. Also notice that there is not even the slightest trace of the normal combustion deposits. That this detonation scrubbed the cylinder absolutely spotlessly clean. You remember I mentioned that light detonation keeps cylinders clean. Heavy detonation keeps them a little too clean. If you take a really close look, you'll see that the spark plugs have pretty much been destroyed, the spark plug insulators. But this is sort of nasty. If we back off a little bit, you can see, of course, you can still see the detonation signatures, but notice the exhaust stains on the bottom aluminum cylinder fin here, and you can almost visualize what happened. The head to barrel junction started to separate up there in the 1 or 2 o'clock position. Exhaust gases started escaping out the crack, heating up the fins and causing the cylinder head temperature indication to rise. Eventually, that fracture propagated itself circumferentially around the junction until it got to the point where the junction was just too weak to hold the cylinder head on, at which point the thing failed dramatically in overload, and combustion stopped, and that was all she wrote. But you can see how by looking at these things, you can pretty much reconstruct exactly the sequence of events and what happened. Here's a picture of the crown of the piston, and again you can see that it's not as close up as the previous one, but you can see that the top of the piston has all of these little tiny micro pits that are signatures of detonation. And then you can see that there's a big chunk of the crown of the piston that melted off in about the 1 o'clock position. You'll get to see the part that melted off in a couple more slides. We've got some really good pictures of this one. This is a side view of the piston, and you can see how the corner of the piston crown actually melted to the point that it totally closed up that top groove where the top compression ring normally sits. You'll see that top compression ring in a minute as well. Now, interestingly enough, when the oil filter was cut open, there was a little bit of little specks of molten aluminum in it, but there wasn't nearly as much metal as you might expect from a violent event like this. This was the oil filter all opened up, and again, there's some metal in there, but not as much metal as you would expect from something this violent. And the reason for that is that the metal that was thrown off, for the most part, was so large that it couldn't get through the suction screen. It couldn't get through the oil pump. It never did get to the filter. It was blocked earlier than that in the oil system by the suction screen that covers the end of the oil pickup tube and basically is there to protect the oil pump from big chunks of metal that have serial numbers on them, and it obviously did its job. So not very much of this metal actually found its way all the way to the oil filter. And what little pieces of metal did get to the oil filter, and normally the suction screen blocks anything larger than about 1/16 of an inch in diameter, the filter could easily capture that stuff. There was no risk of the filter getting clogged and going into bypass. And in fact, one of the things that we checked to make sure that the engine wasn't contaminated, that none of this metal actually got into the oil galleries and started contaminating bearings and stuff, is we pulled off the prop governor to take a close look at the prop governor gasket screen. And if any metal had gotten into the oil galleries, then we would expect to see some of it in that little screen that's in the prop governor gasket. And as you can see, the gasket was absolutely clean as a whistle. There was no metal at all there. So all the metal got caught either by the suction screen, which caught most of it, or the oil filter that caught the little stuff. When the pan was dropped, here's what we found in the oil pan. What you're seeing there is partly metal melted off the piston crown, a big chunk of metal that came off the one half of the piston skirt that fractured. You can see pieces of that of the #1 compression ring in there. You can see a little moon-shaped thing in the lower right-hand corner, which is a part of the piston pin cap. Lots of metal. But it all wound up in the pan, and very little of it got as far as the oil filter, and none of it got any further. So amazingly enough, even though this thing was very destructive, we were able to save the engine and confine the repairs to simply replacing the one cylinder that got compromised. At any rate, those are all the pictures I have for you. Let me just wrap up with a couple of takeaways. Now that you've seen all the good stuff, the first takeaway that I'd like you to leave with is that every piston aircraft engine, whether we're dealing with a J3 Cub or we're dealing with a pressurized twin, every piston aircraft engine needs to have a digital engine monitor installed to instrument the CHT of every cylinder. If this airplane, if you have an airplane that just has a standard factory CHT gauge that is instrumenting the CHT on one cylinder, there's a very little chance that if something like this happens to your engine, you'll be able to detect it until after the cylinder has been destroyed. So we need to be able to monitor cylinder head temperatures on every cylinder, and the way to do that is to install a digital engine monitor. There are all sorts of other great reasons to have a digital engine monitor, but this is one very good one. Every pilot needs to establish some alert levels for CHT and be prepared to take immediate action if those levels are reached. The ones I use in my own airplane, I consider 380 degrees Fahrenheit CHT to be my yellow alert level, which means that if CHT gets higher than 380, I need to do something about it. And I consider 400 degrees my red alert level. If it ever gets to 400 degrees, I have to do something right now, something really aggressive. And you can see from these charts that we've looked at that once CHT passes that 400 degree mark, you don't have a lot of time left to react. You may have as little as a minute. So you need to start taking action right away if cylinder head temperature gets that high. It's extremely helpful to have an engine monitor that has user programmable alarms. For example, the Cirrus SR22 I talked about, its yellow alert, if you will, is hardwired at 420 degrees. Its red alert is hardwired at 460 degrees. Those temperatures are too high, in my opinion, because they don't give you enough warning. I have my yellow alert set at 380 and my red alert set at 400, which I think are more appropriate levels. But some engine monitors allow user programmable alarms where you can actually set the levels where you want the alarms to go off, but many don't. And in fact, the fancy glass cockpit ones, where the engine monitor, the MFD, is the primary, provides the primary engine instrumentation. Typically, those don't allow you to adjust the alarm levels because they're hardwired to whatever the engine manufacturer sets them at. And I think that's a shame, because typically those hardwired alarm levels are too high and they don't give you enough warning. So if you don't have an engine monitor, first of all, shame on you, but second of all, if you're shopping for one of the things you might want to look for in selecting which monitor to install is whether it has user programmable alarms, because I think it's extremely useful to be able to set those alarms at levels that give you enough lead time to actually do something about it. If cylinder head temperature reaches 400 degrees Fahrenheit, which is sort of my red line, my personal red line, and is rising rapidly, cylinder head temperature crossing 400 rising rapidly means you have pre-ignition going on. And if you have pre-ignition going on, you have 1 to 2 minutes before the cylinder will be destroyed. The cylinder and piston will be destroyed. So if you see this, if you see cylinder head temperature reach 400 degrees and rising rapidly, you don't have time to stare at it and think about it and wonder what to do. This has to be a memory item. You need to throttle back to idle immediately. You need to break that thermal runaway process. You need to let whatever's glowing in the cylinder cool down so it doesn't do it anymore. And once cylinder head temperature drops back below 400 degrees Fahrenheit, which is probably a matter of, maybe a half a minute at most, then very cautiously add power back to the extent necessary to sustain controlled flight. Hopefully not more than maybe 50% power, because you don't want to set this thing off again, whatever causing it, and then find an airport and land. But you have to take instantaneous and aggressive action. Well, not instantaneous, but very rapid and aggressive action to break that thermal runaway, that pre-ignition thermal runaway, because it is so fast that unless you act very, very promptly, you're going to lose that cylinder. And of course, and possibly lose the engine if metal winds up getting where you don't want it to be and starts contaminating the engine. Once you're on the ground, after something like this happens, at minimum, you need to have two things done. You need to have somebody stick a borescope in each of the cylinders, looking for detonation signatures, looking for corner melting, looking for the things that I just showed you pictures of. Because those are the telltale signs of detonation pre-ignition. And cutting open the oil filter and inspecting it for metal, seeing how much metal is in there, and determining whether there's any possibility that the metal liberated from the event contaminated the rest of the engine. We hate to see these sorts of things cause an engine to have to be torn down, but sometimes that happens. And so these are the two first steps that are necessary to assess the magnitude of the damage. But most of all, you need to make this part of your memory checklist. You won't have time to think about it when it happens to you. You have to be, spring-loaded to react immediately, because there's very, very little time to make the appropriate actions to save the engine, which is why I call this thing How to Destroy Your Engine in 1 Minute. And with that, Kim, I think we're ready to open it up for Q&A.
Okay, Mike, we got a number of questions that have come in here.
I
let's
bet.
start. Yeah, uh, a number of people kind of wondering about running rich a peak, lean a peak, wondering if that can contribute to these events, detonation or pre-ignition. So can you talk a little bit about running rich a peak and lean a peak, and doing either, can it cause these events to happen?
I can. Obviously, power plant management in general and leaning in particular does have an influence on these things. And here's how that works. Um, there's something that we call detonation margin, which is how close to the point of detonation is a cylinder running. And the amount of detonation margin, it's kind of safety margin, if you will, is a function of mixture, among other things. And the minimum detonation margin occurs at a mixture of approximately 40 to 50 degrees rich a peak. So 40 to 50 degrees rich a peak is the worst place to be in terms of detonation margin. Interestingly enough, there are still a lot of POHs out there that were written in the 60s, 70s, and 80s before we understood this stuff very well, that recommend operating at 50 rich a peak. But we now know that that's the worst place to operate in terms of detonation margin. So unless you're running at, now of course another thing that affects detonation margin is how much power you're running. If you're running 60% power, you've got tons of detonation margin, unless somebody puts some Jet A in your tank or something like that. If you're running at 78% power, you've got a lot less detonation margin. So the two things that really affect detonation margin the most, that at least that the pilot has control over, are percent power and mixture. So unless you're running at a very low power setting, relatively low power setting, say 60% or something lower than that, where you've got so much detonation margin that you don't care, the worst place to be is 50 rich a peak. So you need to either run a whole lot richer than that, say 100 rich a peak or so, or you need to run lean a peak. Either way, you're increasing your detonation margin. It's almost impossible for a cylinder to detonate when it's running, well lean a peak, say 50 lean a peak or something like that, like where I run my airplane. It's also very difficult for a cylinder to detonate if it's running a very rich mixture. It's as I said, the worst spot is right around 40 or 50 rich a peak, and it gets better as you go richer from that, and it gets better as you go leaner from that. So I hope that answers the question.
Great. Lester also wonders, should you go full rich when throttling back to idle if your CHT goes above 400?
Sure, absolutely. In other words, yeah, when you're trying to put out the thermal runaway, absolutely. Throttle back to idle, go full rich, turn on the boost pump, all of the things that would more rapidly break that thermal runaway process, and stay as rich as you can when you bring the partial power back in, because you really don't want whatever was going on there to start happening again. You want to get that airplane on the ground without any further damage. So absolutely, that's a very good point.
Okay. A number of other questions here, kind of dealing with how can I avoid detonation or pre-ignition? What are the things I should be doing to prevent it?
Well, again, if you manage the power plant in a fashion that keeps you in an area of large detonation margin, the probability of this happening is much reduced. Now, there's no guarantees, obviously. I mean, for example, let's say you're running 100 rich a peak because you want to be like really safe. That's fine as long as if it's a fuel-injected engine, for example, as long as one of your fuel nozzles doesn't get plugged up with something. But if it does, you know, that cylinder could wind up in the detonation range. It wasn't anything that you did; it just happened. So, I mean, the emphasis tonight is really how to detect this and how to recover from it, because you never know when it's going to happen. There are things you can do, like leaning properly and so on, to minimize the likelihood of one of these events happening, but you can't prevent it from happening because things go wrong with engines. And so it's no matter what you do, it's really important to have the proper surveillance, if you will, so that if one of these events, one of these abnormal combustion events happens, you know about it right away, and then you know instinctively what to do about it right away. You don't sit there and look at it and say, "Gosh, what should I do?" You have to react immediately.
Beth wonders, what about light detonation, and how should you do this since it's good?
Well, I didn't mean to imply that it was good. We certainly don't want our engines running even in light detonation, simply because if you're running in light detonation, you're really close to the edge of the cliff, and we don't want to be there. So we certainly don't want to try to get the engine to be in light detonation. The point I was trying to make, obviously didn't make it very well, is that detonation is not one of these things like pregnancy. Either you are or you aren't. It comes in all sorts of flavors, and the mild ones aren't destructive, and the intense ones are extremely destructive. But that's not to say that we want to be seeking out light detonation, because if you're in light detonation, you're awfully close to heavy detonation, and you just don't want to be there.
Great point. Neil wonders, can a mag failure result in a spark that occurs way too early, causing a pre-ignition event?
Well, that's interesting. That's a spark going off too early is not what most people would describe as pre-ignition. But to answer the question, yes, that's possible. The failure mode that would cause that, or that can cause that, is when the distributor gear of the magneto fails and sheds a tooth, and so the mag starts firing wrong cylinders at the wrong time. And if any of you have reviewed my my webinar on called All About Magnetos, we got lots of good pictures of those failure cases, of how those gears can fail, and why it's pretty important to open up the mags every 500 hours and inspect them, because there's a lot of somewhat fragile plastic parts in there that can fail and cause some mischief. So although I don't think we would normally refer to it as pre-ignition, the question is there a failure mode that magnetos have that could cause a spark to fire too early? And the answer is yes.
Okay,
and obviously it doesn't matter. It doesn't matter whether the ignition event started too early because the spark went off too early, or because something was acting as a glow plug. No cylinder can survive significantly advanced timing for very long if the ignition event is starting, or if the combustion event starts too early. We had a case of a beautiful Lancer 4P at my airport about a year ago, that the owner, or the builder, spent 10 years and unconscionable amounts of money putting this magnificent airplane together, and he hired the cockpit was wall-to-wall glass. Everything was instrumented up the gazoo. He had his CFI take it up on its first flight, and the CFI came back down, and this $50,000 engine was just literally destroyed. And it turned out that when the engine was hung and the mags were timed, they were timed 10 degrees too far advanced, and 10 degrees of advance on the mag timing was enough to just completely melt this engine down. It was just a slag heap inside. So yes, spark going off too early can definitely do really bad things. And the worst part of that, of course, is that it does it's something like that where you mistime the mag. It does it to all the cylinders at once. It's not just one cylinder that goes into meltdown like these pre-ignition cases tend to be. It's all cylinders at once.
Gotcha. A few questions from folks in their aircraft. George flying a Warrior says that typically on climb out with his 0360, it'll climb up to 430 degrees CHT, and he normally has to throttle, reduce manifold, and bring pressure down and to maintain about 390. He's just wondering if this is normal. But we also got a few people. Mooney is an example that normally runs greater than 400. They're saying 410, 420, 430 in a climb out, and they're saying, you know, it's no big deal for the Mooney. It's just normal business for them. I don't know if you want to make any comments about running normal operations at that high a temperature.
Well, I will make a couple of comments about it. First of all, I'm not comfortable with that for reasons that hopefully are apparent. We've done some fairly interesting research. In our Savvy analysis system, we have about 600,000 flights in our database now. And so we have enough data that we can do a lot of very interesting research, and we've been spending a lot of time crunching those things. On average, it appears that Lycoming powered aircraft have cylinder head temperatures that average about 20 degrees higher than Continental powered aircraft. The CHT red line on Lycoming aircraft is set much higher. It's set at 500 degrees instead of 460. There is some technical basis for that because the head-to-barrel junction on Lycoming cylinders is a little bit more robust than the head-to-barrel junction on Continental cylinders. So one could make an argument, I think, with some validity that the decision temperatures that I use for my airplane, which, as I said, were sort of 380 is yellow and 400 is red, could be advanced by 20 degrees for a Lycoming engine. But certainly anything over 420 on a Lycoming engine is abusive by any measure. And to just say, well, that's just the way it always has been, that's just business as usual, is not an approach that I'm comfortable with. In the case, I can tell you that I've done a lot of work with guys who have RVs that are powered by Lycomings, and a lot of them have cylinder head temperature problems. And one of the things that has been extremely effective in dealing with those is simply retarding the mag timing by a couple of degrees. Lycoming, in its infinite wisdom, set the mag timing for most of those four-cylinder engines at 25 degrees before top dead center, which is very, very aggressive. And it was so aggressive that for the IO360 series, they were having so many problems with excessive CHTs that Lycoming came out with a service bulletin and said, well, we've changed our mind. We're going to back off the timing to 20 instead of 25, which had a huge effect on positive effect on cylinder head temperatures. Unfortunately, that service bulletin that backed off the timing from 25 to 20 only applied to IO360s and only applied to certain IO360s, actually to most. But it didn't apply to the 320s. It didn't apply to the O360s, the carbureted ones, and they're still set at 25. And you know, I hate to argue with Lycoming, but in my opinion, 25 is just too aggressive, and it causes those things to run hotter than they should. Now, for a certificated aircraft, you're required by regulation to time the engine the way the manufacturer says it needs to be timed. And so when I'm talking to the owner of a certificated aircraft that has a Lycoming engine that is having problems with cylinder head temperatures, I say something like, you know, it's not legal for you to retard your timing from the 25 degrees that's on the data plate, but you know, it's amazing how much parallax error you can have when you're doing that timing. When I'm talking to an RV owner, I say, just, you know, back it off a couple of degrees, and it's going to make a huge difference. And they do, and it does. So that's kind of what I have to say on the subject of Lycomings. I think Lycoming has set the ignition spec too aggressive, and it causes those cylinders to run hotter than is good for them. And for some reason, they decided to fix their error on IO360s, but not on any of the other four-cylinder engines that are in the same general family. And that's it. If you're flying experimental, you can time it anywhere you want, and I would recommend, you know, backing it off a little bit from 25. If you're flying a certificated aircraft, I can't advise you to do that. But if it were my airplane, I'd sort of look a little crooked at the flower pot when I was doing the timing. I think I've probably said more than I should on that subject now. So.
Yeah, well said. Enough said. Okay, a couple of questions here. Terry's just wondering if one does not have an engine monitor, are there other signs that detonation is happening? And Sandra says, shame on me, I don't have a CHT monitor. Is there another way to notice that detonation or pre-ignition is occurring?
Well, that's the problem. There isn't. And that's why, I mean, that's one of the many reasons that it's so important to install an engine monitor. I mean, if I was FAA administrator for a day, and don't worry, it's not going to happen, I would make, you know, up-to-date instrumentation mandatory. The requirements of the regulations are you know, were defined 20 years ago, and they just haven't kept up with technology, and it's a shame. But you know, the problem is if you're in a car and the engine starts to detonate, you hear it. It's what's called knocking. Airplane can't hear it. There have been some experiments with knock sensors for aircraft engines, which are basically microphones that are strategically placed on the cylinders, and that listen for that knock. I don't think anybody's gotten anything like that certified. I think there are some FADEX, at least experimental ones, that have knock sensors that listen for that sound and automatically back off the ignition timing if they hear it. But for the most part, there just isn't any way to detect this from the cockpit without a digital engine monitor. The airplanes are just so noisy that you just can't hear it the way you could hear it in a car. And the only practical available solution that we have to that is to have all of the cylinder head temperatures instrumented, and preferably to have some kind of alarm that goes off when the CHTs get too high.
Gotcha. Shahar says on a Continental Geo 300 manual, In the Continental GL300 manual, the Continental states that max cylinder head temp of 525 degrees Fahrenheit for spark plug gasket probe. And then a few other questions have come up about where are you measuring the CHT from. So
Okay,
maybe if you
good
could
stuff.
talk about that.
The GO300 is a sort of an obscure engine. It was used, I guess, on the Cessna Skylark, Cessna 175. I don't have a lot of experience with it, but what I can tell you is that the 460 red line that Continental normally uses on most of its engines is predicated on being measured at the spark plug well, which is a threaded boss on the bottom of the cylinder where you screw a cylinder head temperature probe. If you measure it with a spark plug gasket probe, the temperature normally comes out about 40 degrees hotter than if you had measured it at the spark plug well. And I wouldn't bet my life on this, but if memory serves, I think that the cylinders on a GO300 don't have this threaded boss, so the only place that you can measure them is at the spark plug gasket. So anything that I've said tonight in terms of cylinder head temperatures is predicated on measuring them at the spark plug. I mean at the cylinder head temperature boss on the bottom of the cylinder. And if you are measuring them at a spark plug gasket, you need to add about 40 degrees to all those temperatures. So if 400 degrees was the magic panic button number measured in the usual place, then that number would be more like 440 degrees if you're measuring it at a spark plug gasket probe. And if you add 40 degrees to the 460 degree Continental normal red line, you would get 500, which is but 525 sounds awfully hot to me. I'm not super comfortable with that as even as a last gasp red line. But as I said, I've actually never swung wrenches on a GO300, and I would have to go look up the data on that engine.
So Stephen's wondering, if you have a hot cylinder, does it remain the hottest cylinder through most RPM and power settings?
Well, interesting question, and I won't go too deep into this, but if a cylinder has a higher, if a cylinder has a higher cylinder head temperature than, say, the others, there are two possible reasons that cylinder head temperature could be high. One of them is that cylinder is running leaner than the others, that there's a mixture distribution problem. The other possible reason is that cylinder is not getting as much cooling air as the others. So it's a baffling, a cooling baffle kind of problem. So when we have a hot running cylinder, and the way we figure out whether it's running hot because it's running too lean or because it's running hot because it's not getting enough cooling air is very simple. We take the airplane up on a test flight, and then we note down all the cylinder head temperatures when the engine is running rich at peak, let's say 100 degrees rich at peak. Then we pull back the mixture control to lean at peak, and we write down all the cylinder head temperatures. If the cylinder in question was running hot because it was running too lean, then when we transition from rich at peak to lean at peak, that cylinder will change from being the hottest to being the coolest. If, on the other hand, it's a cooling air problem, then that cylinder will remain hottest regardless of whether we're running rich at peak or lean at peak. So in about 5 minutes during a test flight, it's very easy to determine which of the two reasons a cylinder is running too hot, whether it's a cooling air problem or whether it's a mixture problem. And once you know that, then you can start attacking the problem.
Cool. Jim wonders, does engine run after shutdown idle cutoff, and ignition off indicate detonation or pre-ignition?
Well, I'd sort of have to know what kind of engine it is. An engine that continues to run after you pull a mixture can do that for one of two reasons. But the primary reason is that when you pull a mixture to idle cutoff, it's really not cutting off the fuel supply. I mean, for the engine to continue to run, it has to be getting fuel. And again, depending on whether it's a carbureted engine or a fuel-injected engine, the mechanism for cutting off the fuel supply when you pull the mixture to idle cutoff is a little bit different. But for the engine to continue to run, it basically means it's still getting some fuel. That can be caused by all sorts of things. It can be caused in an injected engine by a problem with what's called a manifold valve. It's the spider thing that's up on top of the engine that splits the fuel up into 4 or 6 equal portions that goes to the nozzles. It can be caused by a leaky primer even with the mixture control and idle cutoff, the engine is still able to get a dribble of fuel through the primer because the primer is not shutting off cleanly. If you have like a pump type primer, so there are a number of reasons. But if the engine is running after you pull it to idle cutoff, it's because it's still getting fuel, and you need to figure out how it's still getting fuel. And there are a couple of different ways that can happen. It's not detonation or pre-ignition that's causing that. It's the fact that you tried to make all the fuel go away and you weren't successful in making all fuel go away.
Gotcha. Michael's wondering, all modern car engines are equipped with detonation sensors. Why are they not available for aircraft engines?
One word, 3 letters, FAA. the certification requirements is this gigantic flywheel that inhibits innovation by making it monumentally expensive and monumentally slow to introduce any kind of new technology. I'm not an expert on what's available in the experimental world, but I would bet you anything that there are some NOx sensor-based FADECs that are experimental right now. I know of no technological reason that NOx sensors couldn't be used on these engines. It's just a certification issue, as far as I know.
And a few questions here about fuel injection, and just want to verify that detonation pre-ignition can also happen on fuel injected as well as carbureted engines, correct?
Absolutely. All of the 3 cases that I showed you were injected engines.
And how about turbocharged engines?
How about it? Anything that can happen in a piston engine can happen faster if it's turbocharged. Yeah, of course. Turbocharged engines are quite vulnerable to these abnormal combustion events. As it happens, none of the 3 that we looked at tonight were turbocharged, but no, absolutely. If anything, turbocharging makes the engine more vulnerable, not less.
Gotcha. Thomas wonders, why did the detonation occur in the second example you gave?
The middle example, the one with the real complicated chart from George, I don't know. It was pre-ignition, by the way, very violent. That's the one with the whole piston. And because I was not personally involved with that particular airplane, I don't know the backstory as to why it happened.
Okay.
In fact, it may not even be known why it happened. One of the problems with pre-ignition events is that they're so violent that they tend to destroy a lot of the evidence. And sometimes, even after a teardown and a very meticulous inspection of the damage, you can't really know exactly what caused it. For example, one of the things that can nucleate preignition, and it commonly does nucleate preignition, is a spark plug, like a cracked nose core insulator on a spark plug. The sharp edges of the crack can start to glow red hot and create a preignition situation. But the preignition event almost always destroys both spark plugs. So after you survey the damage, you see the spark plugs and they're all trashed, but you don't know whether they failed first and caused the preignition, or whether the preignition is what made them is what broke them. So sometimes on these things you just don't even there's no way of actually figuring out the root cause.
Dwayne is wondering, with dual ignition, 2 spark plugs, why wouldn't the flame fronts interfere with each other?
Well, I don't know exactly what interfere means, but they do, burn from 2 initiation points towards the middle. And when we shut off one of the spark plugs by turning off one of the mags, which we do during the pre-flight mag check, and we recommend doing during in-flight mag checks as well, which is a much better test of the ignition system. Shutting off one of the mags dramatically slows down the combustion event, because now it's only being initiated at one point and it has to burn all the way across the combustion chamber, as opposed to being initiated at 2 points and burning sort of towards the middle. There are textbooks that get into the details of the gas flow dynamics that goes on inside a cylinder. There have been lots of studies of these things where a piston got a quartz window installed in it, so you could actually take pictures of what's going on in the combustion chamber. I have to confess that stuff at that level is sort of beyond my level of expertise. I'm not an aeronautical engineer. I'm a humble mechanic.
A very knowledgeable one at that, though, Mike.
but it's important for somebody to know his limits.
Isn't it true for us all? Okay, Tom's wondering, interesting here. So flying about 8,500 feet in a non-turbo engine is safer than 5,000 because of the lower power level? Question mark.
Well, safer in the sense that Mother Nature has throttled the engine back, and so you've got a lot more detonation margin. Safer from that standpoint. Mm-hmm. Maybe safer from the standpoint that if the engine quits, you have a little bit more time to react. Mm-hmm. It's funny. A friend of mine had a power interruption event in a Turbo 210. He was out training with his CFI about 2 weeks ago. The airplane's based up in Denver, and they were up at 8,500 feet, and the terrain was about 6,800, and they were doing some stalls and stall recovers. The engine quit, and he managed to get it back about 200 feet AGL, and his reaction was, next time I practice stalls, I think I'm going to do it a little bit higher.
Altitude is your friend. So RD's wondering, will running lower octane fuel make detonation more likely?
Absolutely, of course. Octane is the measure of the fuel's resistance to detonation. And so absolutely. Nowadays it's pretty hard to find avgas that's anything other than 100 octane, because I don't even think you can get 80 octane anymore. But certainly running MoGas gives you less detonation margin than running avgas, because the MoGas octane is less. The opposite side of the coin, doing things that I see EAB folks do all the time, like installing 9-to-1 compression ratio pistons and stuff to get a little bit more horsepower out of their Lycomings. It reduces detonation margin significantly, and I recommend against doing that sort of thing. It might give you another 3 knots out of the airplane, but you're skating a whole lot closer to the edge of the cliff, and that doesn't make me particularly comfortable.
Okay, other than, Craig's wondering, other than CHT running cooler, is there a performance hit for running timing closer to 20 than 25 on a Lycoming?
There is a very slight reduction in horsepower, but it's so slight that, as I mentioned, Lycoming, just with the stroke of a pen, took a whole slew of IO360s and said, we're going to run them at 20 instead of 25. And the loss of performance was clearly not enough for it to create any sort of certification issue. These engines were, certified to put out 200 horsepower, and obviously even with the timing back off from 25 to 20, which is a big change, they still put out 200 horsepower. Now, it may have been that they were putting out 203 horsepower before, but the amount of performance degradation by reducing mag timing by a few degrees is probably something you would be really hard-pressed to be able to detect on an airspeed indicator. Keep in mind that airspeed varies with the square root of power, so it takes a pretty significant change in power to make a noticeable change in airspeed. And the amount of reduction in power of retarding the mag timing by a couple of degrees is very small. It exists, but it's small.
Okay. Paul's wondering, what about combination of high EGT and low CHT in these types of events? Any issues?
No, there's no limit to EGT. High EGT is not inherently damaging to anything. I did a whole webinar on something called the EGT myth, where I talk about the meaning of EGT, and it's important to understand that EGT is not a measurement of combustion chamber temperature, pressure, or anything. All EGT measures is how much power is wasted out the exhaust valve. Things that cause EGT to go up normally reduce the stress on the engine, not increase it. So high EGT is in no way a problem, other than the fact that it indicates that you're operating inefficiently somehow. That's really what high EGT means. It means that you're wasting a lot of energy out the exhaust pipe rather than converting it into horsepower inside the engine.
Okay, and just to follow up, Donald's wondering if you could just explain one more time, he kind of missed it, the octane is the fuel's measure and to margin from detonation, and how that compares 100 low lead to auto fuel with lower octane.
Yeah, the comparison of avgas octane to auto fuel octane is a little bit complicated, because the auto fuel octane that is posted on the gas pumps at the gas stations use a different octane measurement method than the one that is that's used for avgas. And there's actually a great, if you want to get into this, there's a wonderful Wikipedia page. If you just look up octane on Wikipedia, it talks about all of the different measurement methods and how to convert one into the other and stuff. It's really, really good stuff. I won't try to get into it, other than to say that the 100 octane for avgas and the 91 octane, say, for MoGas, those are not directly comparable with one another, because they're actually on a different a somewhat different scale. But octane is the measure of the fuel's resistance to detonation. And in fact, the way octane is measured at the refinery, because of course when they refine fuel, they have to test it for meeting a whole lot of specs, including the octane spec. And the way they test it for measuring the octane spec is, or to meeting the octane spec, is they put it into what's called an octane engine, which is typically a one-cylinder engine that has a tricked out cylinder head that with a big jack screw on it, so that you can actually make the combustion chamber bigger or smaller by turning this screw, and you can vary the compression ratio of the engine. And they run the sample, the fuel under test, through this octane engine, and they gradually screw down on the cylinder head to increase the compression ratio until they start to hear it knock. And then the compression ratio at which it started knocking gets looked up in a table, and out pops the octane rating. So that's how they actually test octane, is by subjecting the fuel to a higher compression ratio until it starts to knock, and then that particular compression ratio is what tells them what the octane rating is. So it is absolutely a measure. That's what octane is. It's a measure of knock resistance.
Cool. Great way to finish up here, Mike. We've reached the end of the time limit. Any last comments, closing you want to make to the attendees tonight? My counter, I don't know, it's usually a few more than what I show, but I was just about up to 800 attending.
Oh my goodness.
At any one time tonight, so
my
it is
goodness.
a great turnout tonight.
Wow. Well, you know, we have a limit to 1,000, so one of these days, if I come up with like a really out of the park title for one of these webinars, we might wind up with standing room only or something. That would be really cool.
It could be.
At any rate, I just wanted to bring up the next two webinars that I'm doing. The next one is the first Wednesday in July, and we're going to be talking about just kind of going through a summary of the maintenance regulations, both the ones that affect aircraft owners and the ones that affect mechanics. And then the one in August is going to be a week later. It's going to be the second Wednesday of August, because the first Wednesday I'll be on my way back from AirVenture, and it's going to be on the subject of how to resolve owner-mechanic disputes with the minimum of bloodshed and so on and so forth. And so those should both be good sessions, but none of them have a title that's quite as grabby as how to destroy your engine in 1 minute. So I'm going to have to start really working hard on the titles of these things, because there's obviously a correlation between the title and the attendance. And finally, Tim's going to put up the survey in a moment, and he would appreciate it if you take the survey. I would appreciate it if you're interested in subscribing to my monthly newsletter, which is all about ownership and maintenance related kinds of things. Email newsletter that you just check the checkbox on the survey, and we'll put you on the mailing list. And if you don't like it, you can click on the unsubscribe link after you get it and stop subscribing. But we get into some pretty interesting kinds of things in the newsletter, and I think you guys might be interested. So you can subscribe either by clicking the checkbox on the survey that Tim is going to put up, where you can also rate my performance and say how much you hated this and everything, or you can go to savvyaviator.com and you can sign up there. But in any case, I just wanted to extend the invitation to sign up for this monthly newsletter that we put out usually about the middle of the month, and no cost, no obligation, unsubscribe link on every one. So and that's about it, Tim. We'll do this again next month.
Great. And Mike, I want to thank you for the newsletter. I know I've read the last couple issues, and I really enjoyed them, and I think they're well done and very not entertaining, but very engaging articles that you have in there. So good stuff, good information.
Well, thank you. I
Thanks a lot
appreciate
for
that.
putting that out there.
I appreciate that.
You're welcome, and thank you so much, Mike, again for spending the time with this interesting subject tonight.